so it should go decently quick. But it is all going to be words and terms that I use. So if you don't know what those words and terms are, it's going to make things incredibly difficult throughout the unit. Some of them we start off like super easy, things you obviously know, and then we'll move on to things that maybe you've never heard before. A polynomial. Start with that. A polynomial is just like, I don't know, a mathematical expression. You know, in that last unit, we had all those equations, and we had like mx plus b, right? Those were polynomials is what we were creating. And a polynomial could have like lots and lots of things, or it could have very few things, just like one or two. And I'll give you a whole whack of examples so you can see what I'm talking about. There's two parts to any polynomial. So there's letters and there's numbers, which we've seen before, right? We have letters and numbers. The letters are called variables. So just a reminder, letters are variables. And then those letters might have exponents on them. As our polynomials get bigger, they'll obviously have lots more exponents. There are some rules that we have with exponents. We say that our exponents can't be negative. So you can't have like to the power of -1 or something like that. We say that our exponents can't be fractions. And we say that our exponents can't be decimals. So basically, our exponents will always just be counting numbers. We call them natural numbers, like 1, 2, 3, 4, 5, 6, 7, and so on and so forth. You shouldn't see anything crazy, decimals, negatives, anything like that. We also say that we can't have our variables in the denominator of a fraction. So for instance, if you had a polynomial and you saw something like this, like 1 over x, that's not a polynomial because the letter or the variable is in the denominator, which is the bottom. Right? We can't have letters on the bottom of fractions. Awesome. There's special types of polynomials. So there's a few that have definitions, and then there's just a whole whack after that. So we'll start with monomial. Monomial means there's one term. There's three different ways you get monomials. One is if you just have a number, right? Like nice and easy. If you saw something like this, that's a monomial. It's one term. It's one thing. We could also have like negative monomials. So we could have like -3. That's a monomial still. It's just one thing. We could have decimals. And so we could have something like 4.5. That's still a monomial. It's just a number. It's one thing. And we could even have fraction monomials, like 2 over 3. Those are all number monomials. We like never see those. Once we move on past grade 9. You could have variables. So you could have a variable monomial, which means you just have a letter. So for instance, if I had just the letter x, that's a monomial. It's just one thing. That letter x means it's a number. Like it could change to be different numbers. It's a variable. It could change. We could have other letters too. I typically use x. Sometimes we see y's. Right? That's a monomial because it's just y. We might use m. Sometimes you see n. You could technically use any letter you want. We use a lot of x and y. The reason we use a lot of x and y is because then we can graph it, right? X's, y's, makes sense. Sometimes you see different letters because of questions. So for instance, if they talk about the cost of something, they might use the letter C. Any letter could be a variable. Awesome. The monomials that you see the most of are actually products of letters and numbers. So for instance, we see something like this, 2x, that is still a monomial because it's the product of a number and a variable. And we could even add exponents into that. So for instance, 2x squared would be a monomial. It's still just one thing being multiplied together. 2 times x squared. That's what that means. We could do decimals. So we could do something like 0.5 times y. So 0.5y. That's a monomial. It's one thing. And we could also do fractions. So if you could saw something like this, so 3 over 4, I'm going to do a z squared. That's a monomial still. So the 3 divided by 4 is just a number, and it's timesing z squared. That's a monomial. Yeah. Yep. Yeah, that's like where it's all going to lead to. We're even going to do some algebra tiles, stuff like that. Why do we do this? My thing with monomials, the way that I remember if something's a monomial or not, is there should be no addition or subtraction. So if I had like 2 minus x, that is not a monomial because there's a minus sign in there. If I had x plus y, that is not a monomial because there's an addition sign in there. So that's my best way to identify monomials, or one term, is to look for additions and subtractions. Awesome. Another term I use a lot is constant. The constant becomes important, especially in future grades. The constant is if you have a long polynomial, so lots of letters, lots of numbers, and then you have something that's just standing by itself. So a constant is a number and it stands alone. That's kind of what we call it. It's just by itself. For instance, if I had something like 3x plus 5, which we've seen that stuff in past units, this number 5, it's a number by itself. That's the constant. There's no letters. It's just a number by itself. You'll hear it called the constant term. And we'll be like, oh, it's the constant term. Awesome. Looking at these examples, we're going to try to figure out which numbers are the constant. So the constant is the one that's by itself with no letters multiplying by it. In this first one, it's the number 6. 6 is by itself. There's no variable attached to it. If you look at B, the constant in this question is -2. It's by itself. There's no letter attached to it. In the third one, there is no constant. And we've seen that before, right? We saw it last unit. We said if there was no starting value, that's like saying there's no constant. What did we say the constant was? 0. Yeah, we said it was 0. So if there isn't a constant, the constant's 0. Awesome. In the question below, we're going to figure out what the variables are. The variables means the letters. So in the first question, I have a variable of x. It's the only letter in the question. In the second question, my variable is a. Even though there's an a squared and an a, it's still just a as my variable. We're just talking about what letter we're using. In the third one, we have 2 variables. We have variable m, we have variable n. So it's 2 variables. Awesome. Coefficients. I'm not sure if you've heard the term coefficient before. Coefficient. It's the number that's in front of a letter. So the way that it's actually defined is it's the number being multiplied by a variable. So if you look at that first question, we got a, which is 5 times x to the power of 3. That's how we read that. The coefficient would be 5. Because 5 is the number being multiplied by x to the power of 3. On the second one, the coefficient is whatever's being multiplied by the letter. -3 is what's being multiplied by the letter. So -3 is my coefficient. The third question has 2 coefficients. So there's one coefficient on the a squared. There's a 4. And there's another coefficient on the a, which is -7. So we've got constants and coefficients. Constants are numbers that stand alone. There's no letter next to it. Coefficients are the numbers that are in front of the letters. Awesome. We're going to have a couple other special polynomials that we're going to talk about. So we've talked about monomials. We're going to talk about binomials. We're going to talk about trinomials. We're also going to talk about something called degree. Okay, so that's something that's new to us. Have you heard the term degree? I don't think so. Maybe some of you. The term degree is like your highest exponent, pretty much. It's a little more complex than that. We'll do some examples on it, but it usually is our highest exponent. All right, these three. We have monomial, binomial, trinomial. Monomial, we already know. It means one term. Examples of monomials. 2x would be a monomial. That's one term. There's no additions, no subtractions. Another example would be like -3y squared. That's one term. Right? I have -3 times y squared. That's what that means. There's no additions or subtractions. We could also do decimals, 0.5 x to the power of 5. Let's give it a big exponent. Still just one term. Awesome. A binomial. Bi means 2. So this would be 2 terms. Examples of 2 terms would be something like this. 2x plus 3. That is 2 terms. The first term is 2x. Plus the second term is 3. Right? The 2x is one term because there's no addition or subtraction inside that 2x. And then it's plus your other term, which is a constant value of 3. We could have all kinds of binomials. So we could have something like 4x squared minus 15y. That's still a binomial. The first term is 4x squared. The second term is 15y. 2 terms. So there is an addition or subtraction in between 2 things. Trinomial, tri means 3. So now we're looking for 3-term polynomials. 3-term polynomials could look like this. X squared, that's one term, plus x, that's a second term, plus 1, that's my third term. 3 terms. And we could make up as many of these as we want, right? So if we tried another one, we could do something like x, y, that's one term, plus 2y squared, that's a second term, minus z, that's a third term. One term, two terms, three terms. So every addition or subtraction is separating my terms. We only really do the first three. So monomial, binomial, trinomial, those are all special names. So one term, two term, three term. We don't do any more than that. Well, sorry, we do. We don't have a name for any more than that. So if you see something like this, this has one term, two term, three term, four term, five term. We just call that a polynomial of five terms. There's no special name for it. And I wouldn't even usually say of five terms. I would just say that's a polynomial. It's many terms. That's what poly means, many. Awesome. Degrees. So let's talk about degrees for a little bit. Degree is what happens if you add together the exponents of a term. Okay, so it says sum. Sum means add. So you want to add the exponents. But only in one term. Okay, so if you had a polynomial with lots of terms, you wouldn't add all the exponents, you just add the exponents of the term. We'll do some monomials to start. So if you look at this first question, that is a monomial of degree 3. The reason it's degree 3 is because it has an exponent of 3. If you look at B, that would be of degree 1. Because there's an exponent, it's an invisible 1. So C has multiple exponents. There's a 2, there's a 3, and there's a 1. So to figure out the degree, you need to do the sum or add all the exponents. So this would be a degree of 2 plus 3 plus 1. That would be degree 6.
Isn't that one Pythagorean theorem? It looks like Pythagorean theorem, though.
Kind of does, doesn't it?
A squared plus b squared equals c squared times 5.
Yeah. It's not.
I'm sorry, that's what I immediately thought because I hate it.
That's fair. If you look at D, D is a tricky one. D is a constant, meaning there's no letter, no variable. If there's no variable, it's degree 0. It's not degree 1, which sometimes people will think, hey, we know no exponent means degree 1. That's different. Right? So if you look at B and D, these are different because this one has a letter. That's why it's degree 1. This one has no letter. That's why it's degree 0. We don't do a lot with degree in Math 10. Degree starts to become important in grade 11, grade 12. So your teacher will just be like, what's the degree of this thing? And you'd be like, oh, it's degree 2. And then that tells you how to do the question. Or in grade 12, it'll be like, oh, it's degree 4. That means we need to do this. It's degree 3. We need to be able to do this. And it'll like guide what you do. So just learning the definition of it now might seem kind of random, but it will benefit you later on. Okay, example 5. We got a couple more polynomials. We want to try to figure out the degree of those polynomials. The degree is the highest addition for each term. So for instance, if you look at this first one, Each term has a different degree. That one is degree 2. Right? The highest exponent in that term was 2. This one.
Wait, I have like a different exponent that was higher, it would be that one.
Pardon?
You said that's the highest exponent in that one, so this is a different exponent and it's higher?
Then we would add them. Yeah. Yeah. If you look at the middle one, that one's degree 0. And if you look at this one, that one's degree 5. You choose the highest degree to be the degree of that polynomial. So for us, this would be degree 5. Right? So you look at each term and you're picking the highest degree. Typically, it's pretty easy. Like that one like that, you just look for the highest exponent. It's the highest exponent. The next one beside it, we don't see a lot of, but that's a lot trickier. Some people would say that the highest degree is 5. Yeah, but it's actually 6. And why is it 6, Ashley? Yeah, there's an invisible 1 right there, an invisible 1 right here. And to figure out degree, you're adding the exponents for each term. So this first term is degree 5. This second term is also degree 5. And the third term is degree 6. That means this polynomial has a degree of 6. You do each term. Pick the highest one. We don't get a lot of crazy questions like that, but every once in a while. All right, I want you to try to write out the degree of these questions. So I'll let you try it on your own, then I'll go through it. So write out the degree for each question. Okay, so I'll go through it so you can check your answers. So for A, the degree would be adding those exponents. So it'd be 3 plus 9. That means it's degree 12. For B, there's now 2 terms. So I need to do the degree for each term. This one is 3. This one is 2. I picked the highest. The highest degree was 3. So that polynomial has a degree 3. I don't add the 3 and the 2 because those are separate terms, right? They don't combine. If I look at C, I have 3 terms. One here, second one there, third one there. I need to check the degree of all 3 terms. The first one is 7, second one is 5, third one is 2. It's 1 plus 1. The degree of that polynomial is 7. D is a monomial. So this is one big term, right? There's no additions or subtractions in there. So that means I'm adding all of these. 7 plus 10 plus an invisible 1 on that Z would make for 18. E, there's no letter, no variable. No variable means no degree. So that's degree 0. That's typically when people put a degree 1 on. They just think that, oh, no exponent, we put a 1. But there's no letter, so there's no exponent and no letter. Yeah. Okay. If you look at F, we have 2 different terms. So that means we have to calculate degrees both times. This one is 7 plus 4, which is 11. This one's 15. The highest degree is 15. Awesome. Writing polynomials. The way that we write polynomials is we try to go from the highest exponent or the highest degree to the lowest degree, right? That's your goal. So when we write these things, try to write from highest degree to lowest degree. That's like the standard way to write it. It's actually called standard form. So just go highest to lowest. Remember when we were doing y equals mx plus b, like the last week, and we rearranged to put the x first usually? That's because that's the highest degree. That would have been x to the power of 1, which is degree 1. So that went first. The constant had no letter. It goes second. So there was reasoning to why we did it that way. And that's like the standard form to write things. It's not wrong if you do it other ways. It's just not the standard way to write things. That's all. So if we look at these, if we want to rewrite these things in standard form, we want to do the highest degree to the lowest degree. The highest degree right here is this plus x cubed, so that would go first. The next highest thing I have is 2x squared. It would be a plus 2x squared. Now, they didn't have a plus sign in front, but we can imagine that that was a plus or a positive 2. The next highest degree would be this negative 5x. So I would go minus 5x. And the constant term should always go last because it always has degree 0 because there's no letter attached to it. Awesome. If we look at B, B is a little tricky because there's two things with degree 2. Right, we got this guy right here that I'm going to do in blue with the plus 5x squared. That's degree 2. And we got this guy right here, the 7xy. That's also degree 2. So if you get two things that are the same degree, my tiebreaker is whatever one has the highest exponent goes first. So for me, I would put 5x squared first because the x squared power 2 is bigger than any of the other exponents. Even though they're the same degree, I just go with the higher number first. If they had the same amount, then I would just pick one. It wouldn't make a difference. The second thing would be this plus 7xy. And the third thing would be this plus 3y. Highest degree to lowest degree. I want you to try the next 3. Write them from highest degree to lowest degree. Standard form. Okay, I'm going to try to go through a few of them just so you can check your work. If you didn't finish, that's okay. There's a bunch of you guys who didn't finish. If I wanted to write this in standard form, it means highest degree to lowest degree. Looking at my terms, there's 3 different terms here. I have this term, and this term. Okay, identifying the terms is important because then you can start to check the degree of each term. The blue one is degree 6 because it's 5 plus 1. The red one is degree 8 because it's 1 plus 7. And the green one is degree 5. We want to go from highest degree to lowest degree. So the red term should go first. When you're doing that, that minus sign, so it says minus 32xy to the power of 7, that minus sign goes with it. So it becomes negative 32xy to the power of 7. The next highest degree is the blue one. The blue one doesn't have a symbol in front of it, but we need to imagine that it's a positive 18. So it would be like plus 18, x to the 5, y. And then the green one is last, so it's plus 9, x to the power of 5. That negative trick is the hard part. Right? Most people forget to bring the negative with the term. It's a part of it. Awesome. If we look at D, those all have the same degree. They're all degree 1. Right? We have x to the power 1, a to the power 1, g to the power 1. Technically, there is no standard form on how to write that, so anything would actually be acceptable. What I do, and what I would like to see you do, if you ever get things like that where it's all the same degree, just go alphabetical. So for me, I would go 5a minus 7g plus 4x. We just go alphabetical. Honestly, you get a question like that, you're not going to get a standard form question like that. But just in case you ever see me write an answer out and you're like, why did you reorder it? I usually go alphabetical. For E, if I look at these things, this is degree 5. This is also degree 5. My tiebreaker is I go with whichever exponent has the highest exponent. The red one has an exponent 5. The blue one has a highest exponent of 4. So I would go 13x5 first. Then I would go up plus 12x4y. So my tiebreaker is whichever one has the highest exponent goes first. Awesome. Yes, of course. So we've learned a lot of things here, right? We've learned the term variable just means letters. We learned a bunch of polynomials. Polynomials is just a bunch of terms. Terms are things that are multiplied together. Polynomials is then multiple terms added or subtracted together. We've learned degree. Degree is the highest exponent added together in a term. And we learned constant value. I think that's another definition we did. Constant just means a number without a variable or a number without a letter. Awesome. The last thing we're going to do, we're going to look at representing these with algebra tiles. You guys have done algebra tiles before? Yes? No? None at all. Okay. Algebra tiles are just ways of representing polynomials, but with pictures. Its applicability is pretty minuscule after grade 10 because our polynomials just get too big to be able to actually represent them in pictures. But for grade 9 and 10, we can usually actually represent some of them, which is good. So the way that we're going to represent things is when you see a little block like this, that represents a +1, so a +1, and it's a constant. When you see a long, skinny one like this, it represents a +x. So one variable and it's just x. If you see a big square like this, it represents x squared, so to the power of 2. If it's not shaded in, it's negative. So if you look at the ones below, this is one block, but it's not shaded in, so it's -1. If you look at the long skinny block, it's not shaded in, that means it's now a -x. That's fair. And if you look at the third one, it's not shaded in, so it's -x squared. That's how we're going to represent these things. So for instance, if you look right here, we have two polynomials, and they're both represented with algebra tiles. So if I was to look at this first equation, that is -2a squared plus 4a minus 3. That means I should have -2 of the big blocks, right? -2 of the big blocks. That's right here. There's 2 of them. They're both negative, and they're the big blocks. I should then have plus 4a. That means I should have 4 of the long, skinny blocks. If I look, there's my 4 long, skinny blocks. My last thing I have is a -3. So that should be 3 of the little blocks, all negative. That's what I have right here. Yes. Yep. Now, actually, we'll do the next one and then I'll explain this. So if you look at the next polynomial, I have a 3a squared. That means I should have 3 of the big blocks. I then have a -5a. That means I should have -5 of the skinny blocks. And then my last thing I should have is just -2 of the little single blocks, like that. Okay, why this matters. Algebra tiles do help us understand something, and they help us understand like terms, which is a phrase that I've used before, right? I used it last unit when we had things like this. We had y equals 2x minus 1. And people will be like, why isn't that y equals 1x? And people would take these numbers and try to add and subtract them to get 1. Algebra tiles help us understand why we can't do that. So when you have letters or variables and you have different letters or different variables, it means you have different things. So you can't actually combine them together. Looking at these polynomials right now, when this says 3a squared, that means I have 3 of the big blocks. It means I have 3 of something. Then I have negative 5a. That means I have negative 5 of some things. I can't combine these numbers together because they're not like things. Right? If I combine that and said, okay, I have negative 2, you have negative 2 what? These aren't the same thing. I can't add and subtract them. I usually don't use algebra tiles to explain this. I usually use like food because I like food. So I would be like, this represents that I have 3 cookies. Then I lose 5 apples. I would never combine those, right? I still have 3 cookies and I lost 5 apples. I wouldn't say that I have like negative 3 cookie apples. Right? Like, that's insane. They're not like terms. Yeah, like capitals.
I'm not sure if everyone can see this, but the middle block's not in line with the other block, and this block's a bit off from this block.
It is, you're right. Cool. So,
and they're all a bit off. It's somewhat irritating.
I agree. So what's important here with algebra tiles, and like I said, they kind of lose their applicability, is when you have different variables or different exponents on variables. That makes it a different thing. A squareds are not the same thing as a's. We cannot combine them in any way. It's pretty much the only beneficial thing to algebra tiles. It gives us a visual that says a squares are big blocks, a's are skinny blocks. You can't combine them. Okay, we're going to try to model some of these things. Yep. So if we look at this first one right here, we have 4a squared plus 3a minus 7. I'll do the first one for you. So when I read 4a squared, that means I have 4 of the big blocks, and they're all shaded in because they're positive. So 1, 2, 3, and 4. Then I have plus 3a. That means I have 3 of the skinny ones, and they're shaded in because they're positive. So 1, 2, 3. The last thing I have is I have negative 7. Those are constants, so it's just the little individual blocks. They're not shaded in because they're negative. So I have 1, 2, 3, 4, 5, 6, 7. That's how I would represent that polynomial with algebra tiles.
So for 3a, you would have the small ones.
The skinny ones, yeah.
The crouton.
Pardon?
The crouton is small. Not the large, not the long. The skinny ones.
So 3a, a is represented by the skinny ones. If there's no letter, we represent that with little croutons, with little individual blocks. Yeah.
So you don't need like the adding and subtracting symbols when you're doing it.
Yeah. Yep. Yep. I want you to try to do the next one with algebra tiles on your own. So try to do the next 2. Represent them with algebra tiles. My answer is already up on the board, so you can check to see if you're right. The first one had a negative a squared, so that's 1 big block and it's negative. Then I had a plus 3a, that means I have 3 of the long skinny ones. And then I have plus 5, that's plus the 5 little tiny ones. C, I have 5 of the big blocks, and they're all negative. And then I have 3 individuals. I have no skinny ones because there was no X term or no A term. Awesome. I think the biggest thing you could ever gain out of using algebra tiles is they are different things. Right? When I have variables with different exponents, they're different things. We represent squares as squared. Power of 1 is little skinny guy, and the constants is constants. Yeah. This part? You probably have to represent, remember that the big squares are x squares, that the skinny ones are x's, and that the little guys are ones. But you probably don't have to memorize, like, the shading is positive and the non-shading is negative. You could always ask me that, and I'd probably tell you. I think that's fair. But you will have to remember this. Like, squares is the big block. And then to the power of 1 is the skinny. If it helps, the bigger the exponent, the bigger the block. And that's kind of how I remember it. So this is exponent 0, so it's a tiny block. This is exponent 1, so it's a long skinny block. This is exponent 2, so it's a big square. And that's why algebra tiles are limited. So, like, to the power of 3, we could try to do like a 3-dimensional cube or something like that, or a bigger box. I don't know. We have no way of representing like X, Y. Like, if there's 2 letters, we don't really have a way of representing that.
So on the test, there won't be anything but 2.
No, not for algebra tiles, just because we don't go beyond. That's why algebra tiles are so limited. The real only benefit they have is for us understanding what I call like terms. Right? Things are the same or different. Yeah. Yeah, for sure. Okay, the last thing. We're going to go the opposite direction. So we're going to take algebra tiles and create polynomials. So if you look at this first one, I notice that I have 3 of the big boxes, and they're all negative. So I would say I have negative 3x squared. Then I have 2 of these skinny guys. They're both negative. So it'd be negative 2x, because the skinny ones are x's. And then I have 4 of these individuals. Those are my constants. So I say I have plus 4. So you can go the other direction too, right? Algebra tiles could create polynomials.
Is it okay if we don't use the letter X?
Yeah, you could use any letter you want. I just always use X, but if you called that like 3a squared or something, that's fine. If you use Y, that's fine, as long as it's a letter. You could do like smiley faces, I guess, if you want. So if you look at this middle one, we have 4 of the big boxes. So I'd go 4, and then use whatever variable you want. I'll change it. I'll make it y this time. So y squared. If you put x squared, that's correct. Z squared, correct. A squared, correct. Anything squared is good. Then we have 3 of these skinny guys. They're negative, so I have negative 3x. My last one, I got 1, 2, 3, 4, 5, 6 of the long skinny ones. So at 6, and do whatever variable you want. Look, I'll do smiley faces.
Doesn't it have to be a letter?
6 smiley faces. Pardon?
Doesn't have to be a letter.
It should be a letter. I'm just being sarcastic. Yeah, like it's just as long as it's a thing, right? It should have been like 6x. Yeah, that's the proper way to do it. And then minus 4. I have seen questions where they use symbols instead of letters. Wait, so that's kind of why I'm making a joke about it. Like, I've seen them use triangles instead, and they'll be like, you have 4, and then they do a triangle symbol. I don't know why they do that. It just makes it miserable. But as long as you're understanding it's a variable, right? It's just something. So it's 6 smiley faces. I don't know. That'd be cool if they did that on a test.